Hello everyone! Today, we will discuss the chain rule, which is a rule used in calculus to differentiate composite functions. Composite functions are functions that are made up of other functions. This lesson will help us understand what composite functions are and how to differentiate them correctly using the chain rule. Why the chain rule is needed? Not all functions are simple. Some functions involve multiple operations, meaning the variable does not directly affect the function. Instead, it affects one part first, and that change affects the entire function. The chain rule is needed to correctly account for these changes when finding derivatives. What is a composite function? A composite function is formed when one function is placed inside another function. In the example 3x plus 1 squared, the expression inside the parentheses is evaluated first, and then the result is squared. Because the function has layers, we must take the derivative in layers as well. What are the inner and outer functions? The inner function is part of the expression that is evaluated first and is usually closest to the variable. The outer function is applied to the result of the inner function. Identifying this correctly is the most important step in applying the chain rule. Now let's move on to the chain rule formula. If y is equal to f of g of x, then the derivative of y with respect to x is equal to f prime of g of x times g prime of x. The chain rule formula tells us that to find the derivative of a composite function, we must differentiate the outer function first, and then multiply it by the derivative of the inner function. This multiplication ensures that all changes in the function are considered. Now that we know the concepts and the formula for chain rule, let us apply it into some practice problems. For our first example, we have the function y equals the quantity x squared minus x plus 1 raised to the third power. This is a composite function because an entire expression is inside a power. The chain rule is needed here. Step 1. We identify the inner and outer functions. The inner function is the expression inside the parentheses, which is x squared minus x plus 1. The outer function is raising that entire expression to the third power. Step 2. We take the derivative of the outer function. By using the power rule, the exponent 3 comes down and the power becomes 2. We keep the inside expression unchanged for now. Step 3. We multiply by the derivative of the inner function. The derivative of x squared is 2x. The derivative of negative x is negative 1. And the derivative of constant 1 is 0. So now for the step 4, we apply the chain rule. So multiplying this together, our final derivative becomes 3 times the quantity x squared minus x plus 1 squared multiplied by the quantity of 2x minus 1. That completes the derivative using the chain rule. In the second example, we have y equals cosine of the quantity a cubed plus x cubed. First things first, we identify the inner and outer functions. The inner function is a cubed plus x cubed, and the outer function is cosine acting in the expression. For step 2, we begin by differentiating the outer function. The derivative of cosine is negative sign. So we write negative sign of the same inner expression. Then for step 3, we multiply by the derivative of the inner function. The derivative of a cubed is 0 because it is constant with respect to x, and the derivative of x cubed is 3x squared. Leading us to our step 4, which is to apply the chain rule. So the final derivative becomes negative 3x squared times sine of the quantity a cubed plus x cubed. This completes the derivative using the chain rule. For our final example, we have sine of tangent of the square root of sine x. This expression contains several nested functions, so we must apply the chain rule repeatedly. Let u equals sine of x, Next, let v equal the square root of u, which can also be written as u to the 1/2 power. Then let w equal tangent of v, and finally, let y equal sine of w. For step 2, we differentiate each layer. To start, we focus on the outermost function, which is sine. The derivative of sine is cosine, so we write cosine of the entire inner expression unchanged. Next, we differentiate the function inside the sine, which is tangent. The derivative of tangent is secant squared, so we multiply by secant squared of the square root of sine x. After that, we differentiate the square root expression. We will write square root as exponent 1/2, whose derivative becomes 1/2 times the square root of sine x. Finally, we differentiate the innermost function sine x. The derivative of sine is cosine. For step 3, we apply the chain rule repeatedly. Since the function is made up of several layers, we multiply the derivatives one after another. We write dy over dx equals dy over dw times dw over dv times dv over du times du over dx. Now, we substitute the derivatives we found earlier. So y prime equals cosine of tangent of square root of sine x times secant squared of square root of sine x times 1/2 square root of sine x times cosine x. Then, we combine these terms into one expression. So the final answer is cosine x times secant squared of square root of sine x times cosine of tangent of square root of sine x all over 2 square root of sine x. Always remember the step-by-step strategy. No matter how complex a function looks, the steps are always the same. First, identify the outer function. Next, identify the inner function. Third, differentiate the outer function. Fourth, multiply by the derivative of the inner function. And for the fifth, repeat the process if more layers exist. Following the steps carefully makes the chain rule systematic and manageable. Some common mistakes to avoid. Some common mistakes include forgetting to multiply by the derivative of the inner function, or differentiating everything at once, and misidentifying the inner and outer functions. Always slow down and break the function into layers to avoid these errors. To conclude, the chain rule is used to differentiate composite functions by accounting for changes at every level. The same steps apply regardless of complexity. With consistent practice, identifying and applying the chain rule becomes easier and more accurate.